maybe you can do something about it. I was not looking very much at it, and I was not able to do, but that's the reason why it's dedicated to him. And this is a joint work with my ex-master student, Kim Rees. She was very helpful, especially in the first phase of this work, where I was dealing with an approach that stumbled, and she was very useful to get things sorted out and to realize in due time that it was leading nowhere. And then she also had her contribution in the final version. So that's for Kim. Okay. Yeah, no, I have. This is a contents. You see, it's a very short contents. You won't see it again. An introduction, something about reflection and Kummer, and then the proofs. So here we go. What is, this is a result that is under review actually for the proceedings of the last year's conference. So it's in the family. There is take a knot prime and the discriminant of the quadratic field for square root of p, WP, and define the fundamental unit of this field D, quadratic field containing square root of p by t plus u WP. Then the classical statement of the conjecture says that U is not 0 mod P. Actually, this is a very hands-on statement. The statements are equivalent to saying that E is not a local periodic P's power. And beyond that, it has as consequent the fact that the maximal P abelian P ramified extension of D has no torsion. So this is what we will prove. We'll prove that this maximal P abelian P ramified extension of D has no torsion part. Okay. So now, what's the approach? We assume the claim is false, and then I assume that E is a local P to the m's power. So then there is a cyclic P ramified P extension of this degree P to the m over D. I call it F. And on the other side, this E, which is a local P's power, generates over P to the m cyclotomic field a non-ramified abelian extension. And then you go with Leopold reflection on this unramified extension and see that in several steps. The construction implies that F must have a further P-ramified cyclic extension. And this then contradicts with a very tight structure of units and classes in F. So you have a contradiction by class field theory. Now, both the same scheme applies in both proofs, but I will focus on uncanny Chawla for mod Del, which is a case P congruent to 3 mod 4. The quadratic field Q, the real quadratic field Q square root of P, is not in the P cyclotomic field, so you have to join I to climb up to that cyclotomic field. That's the only difference. The approach is otherwise identical. Now we start with notations. Zeta P to the m is a P to the m's root. Km is a P to the m cyclotomic field. And then some local notations, which I introduced for this generic fat K. Omega of K is a maximal abelian P ramified, maximal P abelian actually, P ramified extension of K. And omega underscore is the field of interest, namely the field fixed by a lift of the Galois group of the compositum of all the ZP extensions. So this omega underscore contains the torsion that we are interested in and which we want to show at the end that doesn't exist. In particular, omega is equal to F over D. Okay. I write, as usual, A of K for the primary P part of the class group, and Hilbert class H of K is a maximal P abelian unramified P extension. Again, there's a P missing here. So everything is paired. If the class group, P part of the class group is trivial, then omega underscore K is totally ramified. There's no unramified extension to expect there. Another construction that we need is a completion K prime, I write, because index P is a bad thing in this context. Most of our extensions will have one prime above P, so then this is a extension which has just a completion at one prime above P. In general, it's a product of completions at all the primes above P of your field. Let's see if this works. No, it does not. Okay, now I want to. I apologize, the mouse is pretty difficult. Okay, now we go to radicals. Again, I look at the generic P abelian Kummer extension of degree P to the M, I said. And I suppose that the root of unity is in K, so the extension is really Kummer radical. And if it's cyclic in addition generated by some alpha, then these are just, actually it's an exercise in Washington's book to put it clear. I think it's exercise 913. I used to explain it to my students. Then alpha is a P to the m's power of a radical of an ideal coprime to P times a product of powers of primes above P. So that's how you generate a P ramified Kummer extension. That's how the radicals look like. In addition, if L is totally real and R is 1, so there's no ramified part in the radical, then the class has exactly the order P to the n. Okay, so it cannot be less. This has to do with complex multiplication or complex conjugation, because then on a minus part class you don't have units. So this is how you get this statement, which will be useful. And in addition, if the extension is not just P ramified, but totally unramified, then alpha must be a local P's power, but P to the m's power. Okay. Now, what happens is that in the assumptions, in the last assumptions of this totally real extension with radical which has no ramified part, then the ideal of this class A, which this class A, I don't know if you see the hand, probably you should see this one, the class of the ideal A. So all the ideals, all the primes of this class will split completely in L, and so there's a class in L with norm A and order B. Okay, so that's a crucial point, that you cannot, when reflection works from the minus to the plus part, you cannot get rid of this ideal which generates your radical. You know, it generates your radical. When it generates a radical, it capitulates, but it has split during the same time. So it produced by splitting another class of order P to the n. This will eventually lead to the contradiction. Okay. Yeah, this. Now there is. I work with reflection. So what's the idea? Again, in general setting. Yeah, I have that. In the general setting, you take an extension K over Q with group G, abelian group G to make it simple. And then I look at the group ring over QP to have a nice field of base. And there's a decomposition of one from abelian representations of groups. This decomposition of one comes from traces of totally irreducible characters of G in some extension of QP. In some cases, as the P cyclotomic field, these totally irreducible characters live already in QP. Actually, yeah. Then the main thing about reflection is the following: point 2. I defined a cyclotomic character psi of G, which is a character which tells you to which power a group element maps a root of unity. Okay, that's G of zeta p to the k is sent to zeta p to the k to the power of psi of G. It's a cyclotomic character. And with this, you have the Leopold involution, which is, it's Kummer duality. It is the generalized shape of what in Iwasawa theory we used to call the Iwasawa involution. It is defined as this. You define it on G by sending G to psi of G times G to the -1, and then continue it to an automorphism actually of QPG. This is the evolution, and it's not written here. I tell it in words. What's the game of this Leopold involution? If you imagine the brackets of Kummer duality, you have an automorphism and a radical, and now you act with some group ring element on one side, and you want to pass this action on the other side without changing the result of the Kummer pairing. And the Leopold evolution tells you how the group ring element transforms when going from one side to the other while preserving the value of the pairing. That's what the evolution does. I think. Yeah. Okay. And as a main application, this is an abelian case actually of Leopold's reflection theorem, or a part of Leopold's reflection theorem. I will say what it's all about. Take L over K, an abelian extension of exponent P to the K, and R and X are radical and Galois group. And now there's a relation between the support of the radical and the support of the Galois group. The support is meant in terms of the decomposition of one, which I introduced above. Okay, so an irreducible submodule of QPG is in the support of a module if it does not annihilate that module, period. And the supports of Galois group and radical are dual to each other. That's what this lemma tells us. And this lemma is the first step in the proof of Leopold's reflection theorem. Leopold goes then on to exploit this fact by adding class groups and units and getting an two-sided estimate between the sizes of reflected parts of the class group. We will not use it. So we just use the fact that supports are reflected to each other. Okay, next step, this is an important step. I define F is omega underscore of D. Okay, so remember I had defined F as an P ramified extension of D of degree P to the M, which must exist by class field theory, because a maximal P ramified extension is U, the units, over the completion. I think I skipped, forgive me, I feel I skipped one slide where I introduced units. I don't know, let me see. It's so difficult with this. It's such a nervous mouse. Well, there's something wrong here. Anyhow, let me tell you in words what is not on. I cannot reach that. That's right. So I introduced completion of K, and then I write U of K for the product of the units in these completions, and U1 are the units which are congruent to one of the respective uniformizers. And there's an interesting additional module which I call U prime, which is the kernel of the norm of these units to QP. And this kernel of the norm practically eliminates that. And so this U prime is built in such way that if the field is totally real, then the units under Leopold, which holds in all of our cases, will have the closure of the units will have a finite index in U prime. You see, U will be built from U prime times ZP. ZP corresponds by Artin symbol to the cyclotomic ZP extension, and U prime then embeds properly the completion of the units of the field. The completion of units of the field is, like always, the intersection of E of the units times the global units times the local units to the power P to the N. So it's a topological completion. Okay, so I apologize for this loss of a slide, and we try to get on. Okay, we were here. So the statement is the following. F is this cyclic extension of degree P to the M. It is totally ramified, and I denote by mu the involution of Galois de over Q. Remember, D is a quadratic field, so it has a non-trivial involution, which I lift to F and denote this by mu prime. Okay, and then I take the second torsion of a p abelian p ramified extension omega underscore of f. Okay, and what it turns out that the Galois group of this extension will have a component along 1 minus mu prime as a nidempotent of the group ring of this F, which is not trivial, which is larger than equal to p to the n. And I give a proof. The proof is by reflection, what I was mentioning before. I first take Fm to be F times Km, a totally real Kummer extension generated by a minus part radical. And we can take this radical to be the p to the m's power of an ideal. The reason being that the primes above p are principal in this field. And then I said that Q is in Fm totally split. And then if I take a prime capital Q above small q in Fm, it will have order p to the m. So, and this will generate then again by reflection a further extension, which we do not know yet at this point a priori if it is totally ramified or unramified or what it is, but we will find out soon. Last preparatory lemma, which will be applied by iteration. L over K is a p-ramified extension of totally real fields of degree p, so as simple as possible. The Galois group is generated by me, and I assume there is only one p principal prime p in K above p. And in addition, the class group, the p part of the class group, A of K, is 1. Then these properties are inherited, namely A of L is 1, the prime P ramifies totally in L over K, and the prime above it is again P principal. In fact, I proved that it is in principle, but the P parts are interesting for our work. And the tape cohomology H0 on EL is 1. That means that the units of L surject on the units of K, which is very nice. Subject on the P part always. Now, if I iterate this back to F over D, which is a succession of M such extension, by induction, I find that the properties 1 to 3 hold for F. So the closure of the units, global units in F, subjects on the units of D. So this follows from the theorems of Hilbert. Hilbert 82 and 92 and 93 play a role here, which tell you that if you have a unit in such an extension, unit of norm 1, then you apply Hilbert 90, it's something to the nu minus 1, some alpha to the nu minus 1. And this alpha must, the ideal of this alpha is a ideal which Hilbert calls ambig, which is the product of ramified times capitulated ideals. And the point is here that you have nothing to capitulate from L to K since the class group is 1. and you have only one prime above P, so you have only one possible unit of norm 1, and that is compulsory unit of norm 1, which is derived from Hilbert 91. These results are, I like to derive them directly from Hilbert's theorem. You can work with more fancy results. It's a little bit shorter to use Chevalet's formula, at least for deduction of point 1. But in the end, it all goes back to Hilbert. Okay, so now let's see how I am with my time. Oh, I'm good. I'm good. The aim is to prove that Galois of omega d over d is torsion. Watch that this is omega d over d. It's not underscore omega d over d. Galois of omega, this means that Galois of omega underscore d over d is trivial. So I take this idempotent of the class group of the group ring of F, which is 1 minus mu prime over 2. And I know that it acts on Y. Remember, Y was the second p-unramified extension over Fm. And I know that this class is non-trivial, this Galois group component. Okay. Now I use class group, and so by class group theory, the Galois group of this extension is U prime F over the closure of the units. You see, U prime F comes from the fact that I eliminated the ZP part of the local units. So this is what then local class field theory gives us, because there is only one prime above P. Now again, class field theory tells us in D that the norm defect U prime of D over the norm of U prime of F is isomorphic to Galois of F over D, which is U prime of D over E bar of D. And therefore we deduce, so in other words, the norm of U prime of F has the same defect as E of F. And you see, the norm from F to D of U prime of F on this component 1 minus mu prime is the same as the norm of the closure of the global units in F, which will soon, which implies that the quotient of U prime F over EF, global units closed, is in the kernel on this component epsilon, is in the kernel of the norm. And now I show that it must be trivial. I take a generator of the prime ideal above P in F. Remember that there's only one such guy. And then P to the mu minus 1 will be a unit, a global unit. And on the other hand, I can, U prime of F is a cyclic ZP Galois of F over Q module. So on this component epsilon 1, it is ZP mu cyclic. And I take a generator of this component of U prime. And then the norm will be 1. And it implies that psi is a global unit times alpha to the mu minus 1 for some alpha in the units some alpha in the completion of F, component epsilon 1. But this completion is U prime times my delta to the ZP nu. So it follows that this quotient lays in the augmentation of U prime F over. And then I can apply Nakayama and deduce that U prime F over E bar F is a trivial module. Now, recall by class field theory that U prime F over E bar F1 is precisely the Galois group of the torsion part of the Galois group of the maximal p abelian p ramified extension of F. So, in other words, what we have proved here is that this Galois group must be trivial. Epsilon y must be trivial by class field theory, local class field theory. But previously, we had shown that reflection and the splitting of the radicals force a unramified, a p-ramified extension over F. And this is a contradiction which completes the proof. Now, in the case of the Mordell conjecture, we have the same thing, but as I said, when you embed D in the P to the M cyclotomic extension, you have to join I. And so the idempotents involved in the reflection are slightly different, but the idea of the proof is the same. The core ideal is, you see, what happens is that this small quadratic real quadratic extension is so tiny, it is so restricted, 1 prime above P, no class group, that its properties are inherited along the presumed p abelian p ramified, finite p abelian p ramified extension F, and you get this contradiction because this doesn't allow a growth. The field F by this properties becomes a terminal p-ramified real extension. But on the other side, the mantra of radicals and reflection require a growth of this ramified part. So that's a core of the core idea of the proof. And I think I'm very much well in the time to show you a little bit of diagrams, which show you the same thing, in fact. So I don't know how I make you. Well, do you see me now? Do you see me entirely? I should push this a little bit.
Yeah, we can't see you.
You can see. Can you read the blackboard?
Yeah, just a second, Preda.
Yeah.
Yeah.
Okay.
Wait, just a second. You have to go to the blackboard. Yeah.
So you see, here you have, this is your quadratic field where you join only, we are in the uncanny. You join the square root of P, and if this fundamental unit is a P to the m's power, you immediately get this F, which is the same as omega underscore of D. Let me write this. Okay, which is the torsion part of the maximum p-ramified extension. Okay, and this F, we have shown that it is endowed with this strong properties: 1 prime above P class group is still 1, and the global units jack on the global units from below. Good. And now comes the reflection step. Here you have the cyclotomic set P extension of Q. And you compose B with this QM, which is, and here you have the B to the M's extension, cyclotomic extension. Here you have K1 and here you have Km. So you see Dm is a subfield in Km and D is a subfield in K1 in the case of B1 mod 4, which is the case of uncanny. In the case of Mortel, as I said, it's you have to twist it between it here. Okay, and now this unit E, which we assume to be a local P to the M's power, will necessarily over Km generate a unramified extension, which is this one. Okay, and this unramified extension, you can see where it lives with respect to the composition of Galois K1 over Q. So you only need Galois, the composition of Galois K1 over Q, which is first cyclotomic, P cyclotomic field. So this is you have this consequence and this consequence. Okay, and now my reflection in this field. Okay, so this is an unramified extension. That means that there is a class of order P to the M leading in this, which generates a Galois group of this extension. Okay, so you have a class in Km in this component, and this class generates as radical precisely the lift of F to the M. Okay, here is reflection in the game. Again, so the unit from here generates an unramified extension. The unramified extension implies there is a class which generates a Galois group of this unramified extension, and this class then becomes a radical for a P-ramified extension, which will identify by idempotence with the lift of F to Km. Okay, so this first part is just explanatory. In terms of radicals, you make this extension Kummer extension. So this part is explanatory how Fm comes to be. It comes to be indirectly by the fact that this unit is a local P power and generates an unramified extension. Now the punch is that the radical which generates this Fm is taken from a power of some prime ideals of a class, and these prime ideals split here. So they will generate something, some ramified or unramified extensions further on over this, which will descend here. You see, this extension here is just the lift, so this thing is abelian by identification of idempotence of components of the grouping. So the splitting of the radicals will generate me one additional abelian ramified extension. But when I work out the relationship between U prime and the closure of the units in F, it turns out that U prime and the closure of the units in F coincide on the component of interest. So this extension cannot come to be. So that is what this proof tells us. Okay, so this is for me what I wanted to tell you. We have now, I think, enough time for questions and discussions. In fact, I was very Happy to see that Ramurthy had a talk on this uncanny yesterday. I couldn't see it so early in the morning, but I love Fermat quotients, so I hope to see something written from him to see what connections there are with Fermat quotients. Maybe some new and interesting facts about Fermat quotients can be deduced.